You might be asked for the coordination number in a complex ion, and this is simply the number of coordinate bonds to the central metal ion. Just note it is not the same as the number of ligands, although if you have monodentate ligands then it will be. In this first example you can see that the ligand is a water molecule, and we have 6 of them from the formula, so there are 6 water molecules there. The central metal ion is copper, and the whole complex has a charge of 2+. Now, since the water molecules have no charge, then that 2+ charge must come from the copper, so the metal ion is a copper 2+. In terms of the coordination number, so this is the number of bonds arriving at the copper 2+, well, we've got 6 waters, so there are 6 coordinate bonds, which means the coordination number is simply 6. Let's walk through this table to look at some other examples. So, in the first example, we've got silver with 2 ammonias, so our ligand is an ammonia molecule, and we have 2 of those. The metal is obviously silver, and we can see that the complex has a charge of just +1. The ammonia molecules themselves have no charge, which means that that charge must come just solely from the silver. For the coordination number, we just have 2 ammonias, each coordinating once to the silver, so the coordination number is 2. In the next example, our ligand is chloride ions, and we have 4 chloride ions. Just note they will make a contribution to the overall charge of -4. The central metal ion is a copper. The charge on the overall complex is 2-, and if the ligands are contributing -4, that means the copper must be a 2+. So the -4 and the +2 comes to -2. In terms of the coordination number, well, we've simply got 4 chlorides, each forming a coordinate bond, so the coordination number is 4. Moving on to the next example. The ligand is a cyanide ion, and we have 6 of them in the complex, so they will be contributing a charge of -6 to the complex ion. We can see that the central metal ion is iron. Now, the overall charge is -3, and the cyanides are contributing -6, which means that the ion must be a +3 in this example. For the coordination number, there are just simply 6 monodentate cyanide ions, so the coordinate number is 6. In our next example, we need to be a bit more careful as we encounter a bidentate ligand. So this, you might remember, was the ethane diamine molecule, so a bidentate ligand, so I'm just going to abbreviate it as EN, and we have 3 of these bidentate molecules. This is a neutral ligand, so it makes no overall contribution to the charge. So the central metal ion is nickel, and all of that charge, the 2+, must come from the nickel itself. In terms of the coordination number, we have 3 bidentate molecules, so each of those molecules is forming 2 coordinate bonds with the nickel, so overall the coordination number is 6. In the next example, we have the ethane Dioit ion, and this has a 2- charge, and we have 3 of these bidentate ligands in this complex, so they are making a contribution of -6 to the overall charge. We can see that the central metal is chromium. The complex has a charge of -3. The bidentate ligands are contributing a charge of -6, which means that the chromium itself must be 3+. And for the coordination number, we have 3 bidentate ligands, each forming 2 coordinate bonds with the chromium, so our coordinate number is 6 again. In the final example, we have the EDTA complex. You might remember this has a charge of -4, and it's a hexadentate ligand. So the EDTA with a 4- charge is contributing -4 to the overall charge of the complex. The central metal ion is a copper, and if the charge on the complex is -2, that means that the copper ion here must have a charge of +2. In terms of the coordination number, each EDTA complex, remember it's a hexadentate ligand, so 1 ion of EDTA will form 6 bonds to the copper 2+, so the coordination number is 6.